We're going to begin by looking at Euler circuits. Euler circuits. An Euler circuit for a graph G is a circuit that starts and ends at the same vertex and uses every vertex of G at least once, and uses every edge exactly once. So that's the definition of an Euler circuit. It starts and ends at the same vertex, uses every vertex at least once, and every edge exactly once. Now, you can find out right away if you have an Euler circuit. A graph G has an Euler circuit if and only if G is connected and the degree of every vertex of G is a positive even integer. So if the graph is connected and the degree of every vertex is a positive even integer, then you have an Euler circuit. If it's not connected, obviously you don't have an Euler circuit. And if the degrees of any vertex is not a positive even number, then you don't have a Euler circuit. So let's take a look at a couple of examples here. Let's take a look at this one right here. So does this have an Euler circuit? it's connected. You can go from any vertex to any other vertex. It is connected, but some vertices don't have an even degree. Like you could just, as long as you find one, then that means you're not going to have an Euler circuit. So you could just say V2 has degree 3, not even, no Euler circuit. So in this case, again, you could have picked any one, several of these. This one has degree 3, this one has degree 3. Neither of those are even. That's 3, 3. Now these ones are even. 2, that has degree 2, this has degree 2, this has degree 2. Those ones are okay, but if you have just one that doesn't have even degree, then you don't have an Euler circuit. So this one is no Euler circuit. And how about this one? Take a look at this one. This have an Euler circuit. So it's connected. And let's check the degrees. Degree 2, that's even. How about this one? 1, 2, 3, 4. Degree 4, that's even. Degree 2. This one, 1, 2, 3, 4. Degree 4, that's even. 1, 2, degree 2. 1, 2, 3, 4. Degree 4, even. Degree 2, even. Yes, connected. And all vertices have even degree. So yes. So now let's see, can we find that? Can we find the Euler circuit? Now there's probably more than one way of doing this. Let's see if we can find one. Let's try this. Let's say if we go from V1 to V2, and then V2 to V3, and let's go V3 to V4, and let's go V4 to V7, then V7 to V5, V5 to V2, V2 to V6, V6 to V5, V5 to V4, then V4 back to V1. Yes, that looks like an Euler circuit. Let's just, again, just see what we did here. V1 to V2, V2 to V3, V3 to V4, V4 to V7, V7 to V5, V5 to V2, V2 to V6, V6 to V5, V5 to V4, and V4 back to V1. So notice again, we went through every vertex at least once. You can do more than once if you need to, that's okay. But we went through every vertex at least once. And we got every edge. Notice that there's an arrow on every single edge. And we only used every edge exactly once. Remember the definition of an Euler circuit, you can use it. You have to use every edge exactly one time. And you see there's an arrow on every edge, but no more than two. So that is in fact an Euler circuit. Now we're going to consider Hamiltonian circuits. Hamiltonian circuits. Now, a Hamiltonian circuit is a simple circuit that uses every vertex of a graph exactly once, except for the first and the last. It's a simple circuit that uses every vertex of a graph exactly once, except first and the last. Now, it does not have to use every edge. Now, what criteria can you use to determine if you have a Hamiltonian circuit? Remember, for the Euler circuit, you just had to have the fact that it was connected and every vertex had an even degree. Hamiltonian circuit does a little bit more criteria. If a graph has a Hamiltonian circuit, then the graph has a subgraph, call it H, with these properties. That subgraph H contains every vertex of G of your original graph. H is connected. H has the same, this should say same, same number of vertices and edges. And every vertex of that subgraph has degree 2. So if you have a Hamiltonian circuit, you'll be able to find some subgraph that contains every vertex of G, it's connected, has the same number of vertices and edges, and every vertex of H has degree 2. If you can't find any subgraph with all 4 of these properties, then you do not have a Hamiltonian circuit. Now let's consider this graph. Does this have a Hamiltonian circuit? So that's the question. So now, again, we need to meet those criteria. Those criteria that are required for a Hamiltonian circuit. We have to have a subgraph that covers these 4 things. And usually the best thing to shoot for is to start by seeing if we have a subgraph of degree 2 that's connected. So we'll try to eliminate edges until every vertex has degree 2. If we can do that, then we have a Hamiltonian circle. Remember, the edges don't have to all be covered. So let's go through this and see, like, say, for example, okay, now V1, it already has degree 2. We don't want to mess with that. So V2, it has degree 3. So let's try to eliminate one of these. So we can probably eliminate this one. So now that has degree 2. And let's see. We could probably go over here. Let's see. So now, like for V3, should we take away this one, or this one? Let's see. We can't take away this edge because V4 has degree 2 already. If we take it away, it'll be down to degree 2. So we have to leave this one here. We could take away this one or this one. Let's maybe take away this one. And again, this already has degree 3. Now we have to get rid of another one. So get rid of those two. So here, see the strategy. When we went to V3, we needed to get rid of 2 edges, but we couldn't take this one away because that would give this degree 1, which we need them all to be degree 2. We can't take this one away because that would make V2 degree 2, so we got rid of those 2. Now, what does that leave us up here? So up here, V5 now has degree 1, 2, 3. So we could eliminate this one, but again, that will give V4 degree 1, so we can't get rid of that one. And so we could get rid, no, we can't get rid of this one either, because we can't take this away because V7 already down to degree 2, so we have to eliminate this one. So what do we have? Degree 2, 2, 2, 2, 2, 2, 2. That's it. So, and now when you go through this process and you eliminate those edges to get these all down to degree 2, your Hamiltonian circle will kind of just fall right out. So let's just redraw this without those edges we've eliminated. And so this is going to be the subgraph H. That sort of made this look a little, let me make it look the same as we had. So that would be our subgraph H. Remember, the subgraph has to contain all the vertices, and the degree of every vertex has to be 2, and that's it. Now you can find the Hamiltonian circuit real easily because it's going to be what, just V1, V2, V3, V4, V5, V7, V6, back to V1. So in other words, it would go just like that. So this is our subgraph that contains all the vertices of our original graph and has degree 2 for every vertex. And then, so when you do that, you can find your Hamiltonian circuit real easily. Now, you might want to go back to the original graph so you can put the eliminated vertices back in. Looks something like that. And this is your Hamiltonian circuit. So let's take a look at another one. Let's take a look at this one. Does this have a Hamiltonian circuit? So once again, let's go through the process. So again, V1 has degree 2. Don't want to mess with anything there. And let's see. Do we have any that has degree? So this one, V6 has degree 3. So let's see if we can get it down to 2. So we have a couple of choices. We can actually take this one away, this one, or this one. Now, we don't want to take this one away because V7 is already down to degree 2. And so we could take this one away, or we could take this one away. Probably, let's guess and see if we can do that one. And then, so let's see. So what do we have? So now V6 has degree 2. And let's see. V4 has degree 2. How about this one? Let's see. What can we do over here? For V3, we want to get it down to degree 2. Now we can't take this one away because V4 is already down to degree 2. Can't take this one away because V1 down to degree 2. So let's maybe eliminate this one. And we can probably also eliminate this one. So now this has degree 2, 2. V5, though, has degree 1, 2, 3 still. So we can probably get rid of this one. And I think we're down to degree 2, aren't we, on all of these? Because this is degree 2, 2, 2, 2, 2. So let's make our subgraph. This is the subgraph with those edges eliminated. And once again, you can see, when you make that subgraph, you can kind of see right away where the Hamiltonian circuit is. It's just V1, V2, V7, V6, V5, V4, V3, V1. And you could, so once again, remember, you have to get every vertex exactly once, except the first and the last. So we got it right there. So that's our subgraph. So you kind of work with your subgraph. If you found a subgraph that's connected and these all have degree 2 and has all the original vertices in there, then your Hamiltonian circuit kind of fall right out. Then now you can go back and put your original graph back in. Your original edges, the ones you eliminate, put those back in. And that way you can kind of see how your Hamiltonian circuit appears on your original graph. So let's do one more, see if I have another one here. Let's take a look at this one. Does this have a Hamiltonian circuit? So once again, let's go through and let's see. We need to get, let's start, I don't know where you want to start. Let's start over here. Let's start with V7. Let's get it down to degree 2. So now we can't take that one away because V5 already has degree 2. So we could take away this one or this one. Let's maybe take away this one here. So now this has degree 2, degree 2, degree 2. And this one now has degree 3. So we have to eliminate something here. We can't take this one away because V6 is already down to degree 2. Can't take this one because V7 has degree 2. So we have to take this one away. But look, if we try to take this one away, the graph won't be connected anymore. Remember, that's one of the criteria that the graph had to be connected. You have to be able to go from any vertex to any other vertex. So we'll have to step back. We have to go back here. We have to go back to this original choice here. Remember, we were looking at V7. We chose to get rid of this one. So it looks like we're going to have to get rid of this one here instead. So let's take that edge away and see what we have. So now we have degree 2. Remember, we said we couldn't take this one because V5 already has degree 2. And we tried taking this one away, it didn't work. So, okay, now take that one away. So we have degree 2, degree 2. Now this has degree 3 here. And so now what are we going to do here? How do we get this down to 2? We can't take this one away because V7 already is degree 2. Can't take this one away because the V5 already has degree 2. So we have to get rid of this one. But look, we can't do that either. Because if we take this one away, V1 is already down to degree 2, so we can't take that one away. And also, the graph will be disconnected. So it looks like we're stuck. In our attempt, so we would just did what we did on the last graphs, tried to make these all degree 2. We tried to get this down to 2. We tried this, getting rid of this one, it didn't work. Now this one doesn't work either because when we try to get V6 down to degree 2, we can't take this away, can't take that away, and we can't take that away. So this one is no. So that's the process that you usually go through to find a Hamiltonian circuit. Try to get a subgraph that has all vertices a degree 2 and be connected. If you can't get that, you don't have a Hamiltonian circuit. If you can get it, you know you have a Hamiltonian circuit. Like we saw, the circuit kind of almost falls out. It kind of makes itself.